Okay, Newton explained the tides when he gave his theory of gravity. So we're going to try and understand these tides. And the moon causes the tides. And, it's sort of easy to understand that why the seas would be higher here, but it's kind of hard to understand why the tide is high on this end. Okay, and Newton explained that, and so let's look at this. Okay, so here's how tides happen. Okay, so here's the moon, here's the earth, and we'll exaggerate this picture quite a bit. Okay, oops. So here's the earth. Now the force of gravity, as you know, is given by G_mm by r squared. So the further out you are, the weaker the force. So we'll just make up numbers here. Okay, so let's say the moon attracts this portion of the earth, this part of the earth, with a force of this part of the earth with a force of 100 newtons. I'm just making up numbers. This one is 102 newtons. This one, you're further away, so the force is less, 98 newtons. This guy is 100 newtons, except that in that direction. Or we'll call it a 9. Well, we'll call it 199 newtons. It's this guy is 99 newtons in that direction. Okay. Now what we'll do is we'll set 100 newtons to 0. Okay. So now we'll do the forces again. Now this force has a component in this direction and a component in that direction. Okay. So so 100 newtons is 0. So the force on this guy is a net 2 newtons in that direction. The force on this guy is 2 newtons in that direction. And the force on this guy is in that direction and that direction. And this force was essentially 0. Okay. So now, so what happens to this ocean? So the seas, it gets squished that way, and I've exaggerated it very much. Okay, so the tides, the moon causes the tides, and the tides are a result of the fact that the forces on either ends of the earth are different. Okay, and that's why the ocean bulges. Okay, and so when the moon is there, the ocean is bulged. And as the earth spins, right now this guy had low tide, and in 6 hours he'll be there and he'll have high tide. Okay, so and back again in another 6 hours, so in 12 hours you'll have low tide again. Okay, but of course the moon is not at rest, and the moon also moves, so it turns out that every 13 hours you go from high tide to high tide in every 13 hours, and so on. Okay. All right, so Mr. Newton explained the tides. Now, the question some of you might have is, well, I don't know if you realize this, but so there's a diagram showing you the tides are a result of the differential force between, so if the moon is over here, this portion of the earth is attracted more. Tides are a result of the difference in force between this end and that end. Okay. Now here's an interesting question. The force of the sun on the earth is 200 times that of the moon. So what we're saying is the force that the sun exerts on the moon, on the Earth, is 200 times the force that the moon exerts on the Earth. So the question is, why does the moon cause the tides and not the sun? What matters is, like I said, the difference in the force here. The differential force of the sun is only half of that of the moon, the differential force of the moon. And that's because the moon, even though it's smaller, it's much closer than the sun. So that's why it's this moon that causes the largest effect on the tides. Okay. Again, like I said, it's the differential force that matters. Okay. So we'll see that in the next slide. So here's the differential in the force. So here's the body attracting attracting Earth. See, the sun is, the mass of the sun is 2 times 10 to the 30. That should be kgs, kilograms. And the mass of the moon is 10 to the 20 kilograms. So it's almost a million times more massive, a little more than a million times more massive. And here is the differential force. That's called the tidal force. See, the tidal force of the sun is 5 times 10 to the minus 7, and that of the moon is 11 times 10 to the minus 7. This is 11 times 10 to the minus 7 Newton per kg. Okay, so you see this, the tidal force of the moon is twice, a little more than twice that of the sun. Okay, so what that means is, if this moon is causing a let's say the moon is causing a 6 feet tide, the sun is only causing a 3 feet tide. That's what those numbers mean. Okay. In a simplified way. Okay, so when the sun and the moon are aligned like this, then the tides are the highest, and so either this way or this way. In both these alignments, the tides are the highest. So this is new moon and this is full moon. This is the highest tide. And when the sun and the moon are like this is a neap tide. Their tides are canceling each other. So let's say in a given location, roughly, if the moon is in a given location, if the moon is causing a 6 feet tide, the sun is causing a 3 feet tide. So right now you'll have a 9 feet tide. This would be a 9 feet tide, and this would be a 6 minus 3, 3 foot tide. Okay, so that's what this would be. So these are roughly rough numbers. Okay, so tidal forces can do the following. They can do some damage. Okay, so here's a compact object. This could be a black hole. So a lot of stars are binary star systems. We are unfortunate where we have only one sun, but a lot of star systems are binary star systems. And so let's say this massive star has become a black hole, and as this star is getting older, this will, in a later stage of a star's life, it'll enlarge. Let's say it's starting to become a red giant, and as this stuff gets closer, material will get ripped from there and orbit into will accrete around the black hole and eventually fall down into the black hole. Okay, so tidal force exert between any two bodies, and the effect stretches the bodies along the line between their centers. For some stars, the effect of tidal forces can be catastrophic, and the tidal force in very close binary can be strong enough to rip matter from one star to another. Okay. All right, so we will briefly go over the general theory of relativity. So we talked about gravity. We talked about Newton's law of gravity. Newton's law of gravity was force was every two objects attract each other, and this was the magnitude of the force given by Newton. And again, we know that this is an approximate law, and it works good for small objects, well, for not that massive objects and so on. A more accurate theory is Einstein's general theory of relativity. Okay. But this is not the final theory. A quantum theory of gravity would be the final theory, except that we don't have one of those. Okay. We don't have a quantum theory of gravity yet. All right, so what did Mr. Einstein say? And again, we'll be very brief about it. So this was proposed in Einstein, and this was proposed by Einstein in 1916. Okay, so what Mr. Einstein says is the following: matter and energy, so this is space-time, matter and energy will curve space-time, and then other matter in response to this curvature will move along straight lines in space-time. So this object, when it goes from here to there, that is what is called a geodesic. That is the shortest distance in space-time between these 2 points. So that's what Einstein says. So Einstein says matter and energy will curve space-time, and then other objects move in straight lines in this curved space-times, okay, along geodesics along this space-time. And so this is the equation for which Einstein is famous. What this term tells you is the distribution of matter and energy. That's what this term is related to. And all these terms are related to the curvature of space-time. Okay. So what this equation is telling you is matter and energy curve space-time. Yeah. And once you know the curvature, you can calculate the orbits of other objects. Those objects move in geodesics, along geodesics. Okay, I urge you guys to go check out this YouTube video, and you'll see how space-time is curved. A little demonstration. Okay. So let's talk about black holes briefly. So again, you can take any object and start squeezing it, and you saw that the escape velocity from this object from that distance. So so let's say here's the mass of this object, and r is the radius of the object. The escape velocity from this from the surface of this object is given by that 2g m by r. And now let's say you start squeezing this object. Okay. As r decreases, the escape velocity increases. And you know that nothing can travel faster than the speed of light. And so let's say you squeeze this object inside a radius called rs. This is called a Schwarzschild radius. Okay, so Schwarzschild radius is defined by this fact. So you can calculate the Schwarzschild radius for every mass. Okay, at Schwarzschild radius, at this radius, the escape velocity is become equal to the speed of light. Okay, so if you start squeezing this object, and once you get past the Schwarzschild radius, all the stuff, according to Einstein, everything will fall into the center. Okay. Okay. So beyond at this point, the speed of light, escape velocity is less than the speed of light. At this point, the escape velocity is equal to the speed of light. So at this point, the escape velocity is less than the speed of light. At this point, the escape velocity is equal to the speed of light. And from this point, the escape velocity is greater than the speed of light. Okay. So if you find yourself at this point, there's no escaping. Okay, and that's a black hole. Okay, so black holes are radius at which escape speed equals c is called the Schwarzschild radius. Okay, so that's the Schwarzschild radius. Surface of a sphere with this radius is called the event horizon. This is called an event horizon because you can only be aware of events out of beyond this point. So if you're there, this is your horizon. You can't see these events. And if you're inside there, well, we don't know what's happening to you, but well, anyway, if you're inside here, if you can see all these things. But for outside people, this is the event horizon. You don't know what's going on inside here. You can only see stuff outside of this. Okay, so that's the event horizon. So, and the event horizon, this is how close you can approach and still escape, hopefully. Okay, you would need a pretty powerful rocket to do that. But anyway, so you can calculate, so here's the interesting thing. For any mass, you can calculate the Schwarzschild radius. So what we mean by that is, you can turn, in theory, you can turn any mass into a Schwarzschild radius. You just have to squeeze that mass to within that radius and turn it into a black hole. Okay, so to make the sun a black hole, the Schwarzschild radius for the sun is 3 kilometers. You squeeze the sun into a radius less than 3 kilometers, you can turn it into a black hole. The Schwarzschild radius for the Earth is about, I'm not sure, well, something like 2 centimeters or something like that. So you squeeze the Earth within an inch and you can turn the Earth into a black hole. Okay, so you can turn anything into a black hole. Okay. So it turns out that when stuff falls into a black hole, if it doesn't fall directly in, it'll collect in a disk like this, and that disk is called an accretion disk. And since the gravitational force of black hole is so great, and the tidal forces on all these materials is so high, all this stuff is extremely hot. Okay, and this stuff is emitting X-rays, and from this stuff, from these X-rays, they're characteristic of the black hole. So if material from the normal star can be pulled into the accretion disk around the black hole, so that stuff has fallen into the accretion disk. Okay. So material in the accretion disk is extremely high temperature, and it emits radiation extending into the X-ray. These X-rays are characteristic of the black hole. So the X-rays depend on the mass of the black hole and so on and so forth. Okay. So here's Hubble Space Telescope images of the M87 galaxy, and we believe that's a black hole with at the galaxy's center. Most galaxies have very massive, supermassive black holes at their centers. And I believe our galaxy, you guys can Google this, but our galaxy, Milky Way galaxy, might have several million solar mass black hole at its center. Okay, so here's how we know that there are black holes at centers of galaxies. So you look at if you're looking at stars near the center of a galaxy, these stars are orbiting an unknown mass, unseen mass extremely fast. And you can calculate from their orbital period and orbital radii, you can calculate the mass they're orbiting. So paths of star orbiting about a mass at the center of the Milky Way galaxy. from their orbital motion, it's estimated that a black hole of about 4 million solar masses resides at the center. So a 4 million solar mass black hole resides at the center of our galaxy. Okay. Now Einstein predicted that light would be deflected. A gravitational body would be deflect light. So a light beam is traveling along a geodesic. Okay. So what he's saying is the following. So if a star is here, and here's the sun, here's the earth, starlight is deflected like this. Now our brains are programmed to think that light travels in a straight line. So we will see an image over there. Okay. So even though the star is here, we see an image of it there. Now, of course, the problem is if the sun is that close to the path of the star, starlight is all washed away by sunlight. So how do you verify this? Now, the thing is, there's something called a solar eclipse. So if the moon would come in between the sun, then it would block all sunlight, and then you potentially can measure this. Okay, and that's one of the first things that was done when after Einstein came up with this theory, to test his theory. And the measurements were done, and they found that Einstein was right. Okay, and he became famous after that. All right. So here's another interesting thing. So here's a picture of a quasar. Quasars are the brightest objects out there, and so what they're believed to be is massive black holes at the centers of galaxies, and stuff is falling into them, and that's light from the accretion disk and all that kind of stuff. Anyway, they're very bright objects. Okay, so here's a picture, and it appears that there are two quasars. They're two different objects, but it turns out that they're the same object. You're seeing two images of the same object. And how do we know that they're the same objects? What you can do is you can measure the intensity of light as a function of wavelength. And so you can measure the light curves, and they have the exact same light curve. And so they are the same objects. And so here's what's happening. So here's the quasar, there's the intermediary galaxy, here's the light coming from the galaxy like that. And this beam forms an image there. This beam forms an image there. So those are the two images that you're seeing. Okay. Dark matter. Okay. Let's see. Okay, so what this graph shows you is the following. Okay. Okay, let's say a star is orbiting. Okay. Now the speed of the star, so mv squared by r will depend on g. Oops. Okay. mv squared by r will depend on g m by r squared. Okay. So that's what this equation is telling you, and v is proportional to 1 over root of r. Okay, so what we're saying is, if you're a star out here and you're orbiting, you see all the bright stuff is here, so all the mass is here. And so outside the galaxy, as you go into the edge of the galaxy, your orbital speed should fall off as square root of 1/r. And you see, here are all these stars whose orbital speed is not falling off at all, and in fact staying constant. So what that is telling you is that the mass must be increasing. So there must be mass that you cannot, that's not visible, and that's dark matter. So this orbital graphs, so you can look at a galaxy and measure the speed of stars, orbital speed of stars, and from these speeds, you know for sure that there's some matter out there, and you can't see it, but you can detect its gravity, and so it's called dark matter. Okay, so we've known about dark matter since the 30s or 1940s or so on and so forth. Okay, we've known about dark matter for a long time. Okay, and now we are a little more sophisticated, and so all these guys are images of the same object, and so from all these images, from these duplicate images, we can calculate the dark matter out there, and all this blue stuff is all dark matter. The blue in the image is modeled dark matter. The dark matter would produce the observed images. So again, like I said, these two are identical objects and so on. And so today we know the contents of the universe is 70% dark energy, 25% dark matter, and 5% normal matter. Okay, so what we're saying is all this bright stuff is all normal matter. That's only 5%. The blue stuff is 5 times more than the normal stuff. And then 70% of the universe is dark energy. Okay. All right, so here's one last slide. So we talked about geosynchronous satellites. So there are the geosynchronous satellites. Like I said, the most expensive parking spots. The yellow dots are low Earth orbit satellites, and the red dots are the GPS satellites that are orbiting at about 12,000 miles above the surface of the Earth. Okay, there's way more stuff in orbit now. Okay. Okay, so this story is about the detection of gravitational waves, and that's a long story. We'll have to do it some other time if you're interested. So what I'll do is I'm going to stop the lecture now.